When we look up at the night sky from a quiet hillside or a darkened room, we are met with a sense of profound stillness. The stars appear as fixed points of cold, diamond light, pinned against a velvet backdrop that seems unchanging. The constellations rise and set with the rhythm of a clock, predictable and serene. It is easy, in this quiet observation, to believe that the universe is a place of peace, a vast and silent ocean where matter drifts slowly through the dark. But this tranquility is an illusion born of distance and time. If our eyes could see beyond the narrow band of visible light, if we could perceive the high-energy radiation that floods the cosmos, the sky would not look peaceful at all. It would look like a chaotic fireworks display of unimaginable violence. We are embarking on a journey to find the most powerful thing in the universe. It is a search that requires us to define what we mean by power. Is it the object with the most crushing gravity? Is it the force that stretches the fabric of space itself? Or is it the ability to release the greatest amount of energy in the shortest amount of time? If we define power by the sheer intensity of a single event, by the capability to outshine entire galaxies and release more energy in a few seconds than our sun will emit in its entire 10 billion-year lifetime, then we must turn our attention to the edge of the visible universe. We must look for the blinding flash of a gamma-ray burst. These events are the heavyweights of the transient universe. They are the brightest electromagnetic events known to occur, second only to the Big Bang itself. To understand a gamma-ray burst, one must first try to comprehend the scale of energy involved, a task that strains the limits of human imagination. Picture our sun, a burning sphere of plasma so large that 1 million Earths could fit inside it. It has been burning for nearly 5 billion years, radiating heat and light that sustains all life on our planet, and it will continue to do so for another 5 billion years. Now, imagine taking every single photon of light, every joule of heat, and every particle of energy the sun will ever produce from its birth to its death, and compressing all of that history into a single concentrated beam lasting no longer than 20 seconds. That is the scale of power we are discussing. For decades, these bursts were a mystery. They were discovered not by astronomers looking at the stars, but by satellites designed to look down at the Earth to monitor for nuclear tests during the Cold War. These satellites, waiting for the signature of a terrestrial explosion, instead detected massive spikes of gamma radiation coming from deep space. At first, the data was baffling. The flashes were random, coming from all directions, ignoring the plane of our own Milky Way galaxy. This suggested they were not local, but were originating from the deepest, farthest reaches of the cosmos. It meant that for them to appear so bright to our detectors, their intrinsic power had to be terrifyingly high. The source of this power lies in the dramatic death of a true giant. While ordinary stars like our sun end their lives relatively quietly, shedding their outer layers to form beautiful planetary nebulae, the universe's most massive stars die with a violence that shakes the foundations of the galaxy around them. These are stars with masses 20, 30, or even 50 times that of the sun. They live fast and die young, burning through their nuclear fuel with a voracious appetite. Throughout their short lives, they are engaged in a constant war between gravity trying to crush them inward and the explosive pressure of nuclear fusion pushing outward. For millions of years this balance holds, but eventually the fuel runs out. When the core of such a massive star is finally depleted of elements, it can fuse to create energy, the stalemate ends. Gravity, waiting patiently for millions of years, instantly wins. In a fraction of a second, the iron core of the star, a sphere roughly the size of a city, collapses inward at a quarter of the speed of light. It is arguably the most catastrophic structural failure in nature. The core crushes down, becoming denser than an atomic nucleus. In many cases, this collapse does not stop at a neutron star. The mass is too great, the gravity too overwhelming. The core continues to fall in on itself, piercing through the fabric of space-time to form a black hole. This is the engine of the gamma-ray burst, the birth of a black hole in the heart of a dying star. But the black hole does not sit idly. As the rest of the star's material tries to follow the core inward, it begins to swirl. The gas and plasma, finding no room to fall directly in, form a superheated disk rotating at incredible speeds around the newborn black hole. Friction within this disk heats the material to billions of degrees, while the twisting magnetic fields generated by the chaotic motion begin to act like a cosmic railgun. This is where the true power is generated. The magnetic fields, wound up tight by the spinning black hole, launch jets of superheated particles outward from the poles of the star. These jets are not sprays of water. They are focused beams of plasma moving at 99.9999% the speed of light. They are drilling mechanisms. The jets slam into the layers of the dying star that are still collapsing inward. It is a race against time. The jet must punch its way through the entire body of the star before the star collapses completely. When the jet breaks through the surface of the star, the energy is released into the cosmos. This is the moment of the gamma-ray burst. The energy is not emitted in a sphere like a light bulb. It is focused into a narrow beam, like a lighthouse. If you happen to be in the path of this beam, you see a flash of intensity that defies logic. This focusing is what makes them appear so bright to us. Even across billions of light years, it is a sniper shot across the universe. The radiation produced in these jets is of the highest energy known, gamma rays. These are photons with such short wavelengths and high frequencies that they pass through ordinary matter as if it were not there. They carry enough energy to strip electrons from atoms, to break chemical bonds, and to sterilize any biological material they encounter. If a gamma-ray burst were to occur within our own galaxy, say within a few thousand light-years of Earth, and its beam was pointed directly at us, the consequences would be severe. The gamma rays would strip away the ozone layer in our atmosphere, exposing the surface to lethal solar ultraviolet radiation. It would be a silent extinction, arriving at the speed of light, with no warning until the sky began to change. However, we are protected by the vast distances of space. Most of the bursts we detect come from the early universe, from galaxies so far away that their light has taken billions of years to reach us. They are the ghosts of ancient stars that died long before the Earth was formed. When we detect a gamma-ray burst today, we are witnessing a tragedy that happened when the universe was young. We are seeing the final scream of a star that existed in a time when the cosmos was denser and more chaotic. The duration of these bursts varies. Some are long, lasting for a minute or more, sustained by the feeding of the black hole on the stellar debris. Others are short, lasting less than 2 seconds. These short bursts are thought to have a different origin, likely the collision of 2 neutron stars, a violent merger we will explore later in our journey. But the long bursts, the ones born from the collapse of massive stars, are the true titans of luminosity. Recently, astronomers witnessed a burst so bright it saturated the detectors designed to measure it. It was named the Boat, the brightest of all time. It occurred in a galaxy 2 billion light-years away, which is relatively close in cosmic terms. The energy it released was so intense that it disturbed the upper atmosphere of Earth, ionizing particles high above our heads. It was a stark reminder that although space is vast, it is connected. An event billions of kilometers away can still reach out and touch our world with a ghostly finger of energy. The afterglow of a gamma-ray burst tells its own story. Once the initial flash of gamma radiation fades, the jet continues to plow into the interstellar gas surrounding the dead star. This collision creates a shock wave, not unlike a sonic boom, which heats the surrounding gas and causes it to glow. This afterglow fades from X-rays to visible light, and finally to radio waves over days, weeks, or even months. It is through this fading light that astronomers can pinpoint the location of the burst and identify the galaxy that hosted it. Often, they find a galaxy teeming with star formation, a factory of massive stars, confirming that these bursts are indeed linked to the deaths of the very biggest suns. There is something humbling about the physics of these events. The energy is generated in a region only a few hundred kilometers across, the size of a small province or state, yet it outshines the entire visible universe. It demonstrates that power in the cosmos is not always about size. It is about density, efficiency, and the extreme warping of physical laws. The conversion of gravitational potential energy into radiation during the collapse of a star is the most efficient energy production mechanism in the universe, far surpassing the nuclear fusion that powers the stars during their lives. As we visualize the jet of a gamma-ray burst tearing through the darkness, we must also appreciate the silence. In the vacuum of space, this cataclysm makes no sound. There is no roar of the explosion, no tearing of the stellar envelope. There is only the silent projection of light, racing outward at the ultimate speed limit. To an observer nearby, if they could survive the radiation, it would be a blinding visual spectacle, a new star appearing from nowhere, brighter than the rest of the sky, turning the night into a searing day, and then slowly fading back into the black. The collimation of the beam, the way it stays narrow over vast distances, is a testament to the power of the magnetic fields that shape it. These fields are invisible cages holding the plasma together against its natural tendency to spread out. They are spun from the rotation of the black hole, twisting like rubber bands until they snap or launch the material outward. It is a mechanism of pure geometry and physics, operating on a scale that renders our human concerns microscopic. Yet, despite their destructive power, gamma-ray bursts are also creators. The shock waves they send out can compress gas clouds in their host galaxies, triggering the collapse of new nebulae and the birth of new stars. The heavy elements forged in the dying star and ejected in the explosion are scattered into the cosmos, seeding the galaxy with the oxygen, carbon, and iron that will eventually make up planets and, perhaps, living things. It is a cycle of destruction and creation driven by the most powerful explosions in existence. But is a gamma-ray burst the most powerful thing? It certainly holds the title for the most intense flash of electromagnetic radiation. It is the king of brightness. However, its power is transient. It lasts for seconds or minutes, a brief candle in the dark. Once the fuel is consumed, once the star has fully collapsed and the black hole has cleared its immediate surroundings, the burst ends. The jet fades, the light dims. The darkness returns, leaving only a remnant behind. This remnant, the object left in the wake of the explosion, possesses a different kind of power. It is a power not of outward explosion, but of inward intensity. A power that does not fade over seconds, but persists for eons. The collapse that triggers the gamma-ray burst sometimes leaves behind a neutron star with a magnetic field so intense it defies comprehension. These are the magnetars, cosmic beacons that silently scream with magnetic fury. While the gamma-ray burst is a flashbulb, the magnetar is a permanent engine of distortion, a localized knot of physics so extreme that it warps the atoms of anything that dares to approach it. As we move from the fleeting brilliance of the burst to the enduring, crushing presence of the remnant, we begin to see that power comes in many forms. The gamma-ray burst is the power of release, of energy unbound. But there is another power, one that is tightly held, coiled, and waiting. To understand this, we must journey closer to these dense cores, to the objects that can strip information from the universe and reset the magnetic alignment of an entire galaxy sector. We leave behind the fading afterglow of the great explosion. The gas cools, the shockwave dissipates into the void, and the galaxy returns to its slow rotation. But in the center of the debris field, something is spinning. Something small, heavy, and terrifyingly magnetic. It is here that our search continues, moving from the blinding light of the explosion to the invisible, silent, and crushing grip of the magnetar. The universe has shown us its flash. Now it will show us its grip. Deep within the expanding nebula of a shattered star, the violence of the supernova has long since faded. The shock waves have moved on, carrying the heavy elements of creation into the dark void, leaving behind a silence that feels absolute. But in the exact center of this debris field, hidden by swirling veils of dust and cooling gas, lies an object of density and intensity that defies the logic of the everyday world. It is a neutron star, the crushed heart of a giant, spinning rapidly in the cold blackness. Among these dense remnants, there exists a rare and spectacular class of object, a celestial body that wields a force unlike any other. This is the magnetar. To understand the magnetar, we must first understand the object from which it is made. A neutron star is a sphere roughly 20 kilometers in diameter, no larger than a sprawling modern city. Yet, within this small, compressed space, it holds a mass greater than that of our sun. It is a place where matter has been crushed beyond recognition. The protons and electrons that make up the atoms in our bodies, our planet, and our stars have been squeezed together so violently that they have merged to become neutrons. The star is, in essence, one gigantic atomic nucleus, a city-sized drop of nuclear matter held together by gravity, so strong that the human mind struggles to grasp it. If you were to stand on the surface of a neutron star, an impossible feat, as the gravity would instantly reduce you to a thin layer of atoms, you would find yourself on a landscape of terrifying smoothness. The gravity is 100 billion times stronger than that of Earth. Under such crushing weight, no mountain can stand. The highest features on the surface are mountains no taller than a few millimeters. The surface is a solid crust of iron, arranged in a crystal lattice, harder and denser than anything in the known universe. Beneath this crust lies a sea of superfluid neutrons, a frictionless ocean of particles swirling in silence. But for a magnetar, density is not its most defining feature. Its true power lies in the invisible field that surrounds it, When the parent star collapsed, the magnetic field that threaded through its core was not lost. Instead, it was compressed, concentrated, and amplified 1,000,000,000,000 times over. A magnetar possesses a magnetic field so intense that it becomes a physical entity, a force that dictates the structure of space and matter around it. On Earth, we are accustomed to magnetic fields that are gentle. The Earth's field guides our compass needles and protects us from the solar wind, but we walk through it without feeling a thing. Even the strongest magnets created in our laboratories, capable of lifting cars or guiding particle beams, are ghostly whispers compared to the scream of a magnetar. The magnetic field of these cosmic giants is 1,000 trillion times stronger than that of the Earth. It is a number so large it loses meaning, so we must look at its effects to understand its power. This magnetic field is so strong that it becomes hostile to the very chemistry of life. If a spaceship were to approach a magnetar, the danger would not initially come from radiation or gravity, but from the magnetism itself. At a distance of 1,000 kilometers, still far from the surface, the magnetic field would be strong enough to interact with the water molecules in a human body. It would distort the electron clouds that orbit the nuclei of your atoms. In our universe, atoms are typically spherical, with electrons buzzing around the center in a cloud. This shape allows for the chemical bonds that build DNA, proteins, and cells. But near a magnetar, the magnetic force is so dominant that it overpowers the electric forces holding the atom together. It squeezes the electron clouds into long, thin needles aligned with the magnetic field lines. The chemistry we know becomes impossible. Molecular bonds shatter. Matter dissolves into a strange, elongated vapor. To approach a magnetar is to have the very building blocks of your existence unraveled by the sheer force of magnetism. This invisible cage of magnetism does not just affect approaching matter. It affects the vacuum of empty space itself. According to quantum electrodynamics, the vacuum is not truly empty but is filled with virtual particles popping in and out of existence. In the presence of a magnetar's field, this vacuum becomes birefringent. The empty space acts like a prism or a crystal, splitting light and changing its polarization. The magnetar is so powerful it modifies the optical properties of the nothingness that surrounds it, creating a region of space where light itself must obey the rules of the magnetic king. The life of a magnetar is not a peaceful one. The magnetic field is not static. It is twisting and turning, rooted in the superfluid interior of the star. As the star spins, the magnetic field lines can become tangled, winding up like a rubber band that is stretched too far. The crust of the star, that solid shell of iron, is forced to hold back this immense magnetic pressure. It resists, holding firm against the stress for years or centuries. But eventually, the strain becomes too great. When the crust fails, it cracks. This is a starquake, a seismic event on a scale that dwarfs anything Earth has ever experienced. On our planet, an earthquake involves the shifting of rock plates. On a magnetar, a starquake is the fracturing of the densest material in the universe. When the crust snaps, the tangled magnetic field lines above it are suddenly released. They snap back into a lower energy state, a process known as magnetic reconnection. This snap releases an explosion of energy that can briefly outshine a galaxy. We call these events giant flares. They are storms of high-energy X-rays and gamma rays that blast outward from the star, sweeping through the solar system. We do not just hypothesize these events, we have felt them. On December 27th, In the year 2004, invisible waves of energy washed over our solar system. They had traveled for 50,000 years, crossing the vast gulf of the Milky Way galaxy. They originated from a magnetar known as SGR 1806-20. When the wavefront hit Earth, it was detected by satellites and observatories. But it did more than just trigger sensors. The flare was so powerful that it physically compressed the Earth's magnetic field. It ionized the upper atmosphere, causing it to swell and glow. For a brief moment, a dead star on the other side of the galaxy reached out and touched our planet's atmosphere. If this flare had originated from a magnetar within 10 light-years of Earth, rather than 50,000, it would have been an extinction-level event. It would have stripped away our ozone layer and bathed the surface in lethal radiation. It is a sobering thought that such power exists, lurking in the dark corners of the Milky Way, silent until the moment the crust cracks. Yet, there is a strange beauty to these objects. They are the strongest magnets in the cosmos, yet they are incredibly small. They spin with a precision that rivals the best atomic clocks, yet their interiors are chaotic storms of superfluidity. They are lighthouses of the invisible spectrum, sweeping beams of X-rays across the sky as they rotate. The magnetic field of a magnetar is also a reservoir of energy. Unlike normal pulsars, which are powered by their rotation, slowing down over time as they lose momentum, magnetars are powered by the decay of their magnetic fields. This creates a unique lifespan. The magnetic field is so intense that it acts as a brake, dragging on the star and slowing its spin. A magnetar might start its life spinning hundreds of times a second, but within a few thousand years, a blink of an eye in cosmic time, it slows down to a rotation of once every few seconds. As the spin slows and the magnetic field dissipates its energy through flares and steady X-ray glowing, the magnetar begins to age. The furious activity of its youth fades. The starquakes become less frequent. The giant flares cease. The magnetar slowly transforms into a normal, albeit still hot and heavy, neutron star. It enters a long retirement, cooling over billions of years, fading from the view of our telescopes, becoming just another dark, heavy ghost drifting through the interstellar night. But during its brief, 10,000-year reign as a magnetar, it represents a pinnacle of physical extremism. It shows us that magnetism is not just a force that sticks a note to a refrigerator or points a compass north. It is a fundamental aspect of the universe that, when concentrated, becomes a dominant ruler of reality. It can hold back the collapse of a star, it can shatter the crust of a world, and it can rewrite the shape of atoms. As we contemplate the magnetar floating in the silence of deep space, we are reminded of the hidden complexity of the vacuum. We usually think of space as empty, a void to be traversed. But around a magnetar, space is thick. It is textured with magnetic field lines that are as real and solid as stone pillars. To travel through that space would be to push against the grain of the universe itself. This magnetic power is static, in a sense. It is a trap, a cage, a localized distortion. It is immense, but it is confined to the immediate vicinity of the dead star. To find a power that is more active, more voracious, and capable of influencing the structure of entire galaxies, we must look elsewhere. We must look away from the single dead stars and toward the centers of the great galactic cities. We must find an engine that does not just store energy, but consumes matter on a scale that creates a beacon visible across the entire observable universe. We are leaving the realm of the dense, magnetic ghosts and moving toward the great devourers. We are setting our course for the blinding heart of a quasar, where gravity and friction combine to create a firestorm that can outshine 1,000,000,000,000 suns. The magnetar has shown us the power of holding on, of tension and release. The quasar will show us the power of falling in. It is a transition from the magnetic to the gravitational, from the small and silent to the large and loud. As the magnetic field lines fade behind us, we see a glow on the horizon, a light so bright it masks the monster lurking within. As we drift away from the singular magnetic fury of the neutron star, we find ourselves moving across the vast, empty stretches of intergalactic space. The vast stars of our own galaxy fall behind us, merging into a soft, luminous haze. We are entering the deep universe, the realm where galaxies themselves are merely dust motes dancing in the dark. Here, amidst the silent swarm of island universes, we are looking for a light that defies explanation. We are looking for an object that, from a distance, appears to be a single, modest star, yet possesses the brilliance of 1,000,000,000,000 suns. This is the paradox of the quasar. For decades, astronomers who studied the sky were baffled by these objects. Through their telescopes, they saw points of light that looked exactly like the stars in our own Milky Way. They were pinpoints, sharp and unwavering. But when they analyzed the light, breaking it down into a rainbow spectrum to read its chemical signature, they found something impossible. The light was shifted toward the red end of the spectrum to a degree that suggested these objects were not neighbors, but were receding from us at tremendous speeds. They were located at the very edge of the observable cosmos, billions of light years away. For a single point of light to be visible across such a staggering abyss, it could not be a normal star. It had to be something else entirely. It had to be a beacon of such intensity that it could outshine the entire galaxy of stars in which it resided. We now know that a quasar is not a star at all. It is the blazing heart of a young galaxy, powered by the most efficient energy-generating mechanism in the known universe, the feeding of a supermassive black hole. To understand the scale of a quasar, we must recalibrate our sense of size. The black holes we met earlier, those born from the deaths of single stars, are heavy, but they are physically small, mere city-sized specks. The monster lurking in the center of a quasar is a different breed altogether. These are supermassive black holes. They contain the mass of millions, sometimes billions, of suns. They are not born from a single collapse, but are grown over eons, formed from the merger of smaller holes and the endless consumption of gas and dust. They are the gravitational anchors of the universe. If we were to place one of these giants at the center of our solar system, its event horizon, the point of no return, would not just swallow the sun. It would extend out past the orbit of Earth, past Mars, perhaps even reaching the realm of the gas giants, Jupiter and Saturn. It is a hole in reality so vast that it creates a localized region of darkness larger than our entire planetary neighborhood. But a quasar is not defined by darkness. It is defined by light. A black hole by itself is invisible. It creates light only when it feeds. In the crowded, chaotic centers of young galaxies, gas clouds and dust lanes are constantly being pulled inward by the black hole's immense gravity. However, this material cannot fall straight in. It carries momentum, the spin of the galaxy itself. As it approaches the abyss, it is whipped into a frenzy, forming a vast, flat structure known as an accretion disk. This disk is the true engine of the quasar. It is a cosmic whirlpool, a spiraling storm of gas waiting to be consumed. As the gas spirals closer to the event horizon, it moves faster and faster, approaching the speed of light. The layers of gas rub against each other, creating friction on a scale that is difficult to comprehend. Imagine rubbing your hands together to create warmth on a cold day. Now, imagine that friction amplified by the gravity of 1 billion suns. The gas does not just get hot. It glows with a ferocity that strips electrons from atoms and releases a torrent of X-rays and ultraviolet light. The temperature in the inner regions of this disk reaches millions of degrees. It is a dynamo that converts gravitational potential energy, the energy of falling, into pure radiation. This process is terrifyingly efficient. When a star like our Sun burns hydrogen into helium, it converts only a tiny fraction, less than 1%, of its mass into energy. It is a wasteful engine. A quasar, by contrast, is a master of efficiency. As matter falls into the gravity well of the black hole, up to 40% of its mass is converted directly into energy before it vanishes across the event horizon. It is the ultimate extraction of power from matter. This is why a quasar shines so brightly. A region no larger than our solar system releases more light than a galaxy containing 200 billion stars. If a quasar were situated at the center of our Milky Way, night would cease to exist on Earth. The sky would be dominated by a second sun, a searing eye of cyclopean light that would cast shadows even at noon and render the other stars invisible. The radiation would likely sterilize our galaxy, stripping away the atmospheres of planets thousands of light years away. We are fortunate that the nearest quasars are billions of light years distant, relics of a younger, more violent universe. The power of a quasar is not limited to the light it emits. It is also a kinetic engine. Not all the material in the accretion disk falls into the black hole. The magnetic fields in this chaotic environment are twisted and amplified, much like those of the magnetar, but on a grander scale. These fields act as slingshots. They capture some of the ionized gas before it crosses the point of no return and channel it toward the poles of the spinning black hole. From these poles, massive jets of matter are launched into space. These are not the fleeting bursts of the gamma-ray explosion. These are sustained fire hoses of plasma, blasting outward at 99% the speed of light. These jets can stretch for hundreds of thousands of light years, punching their way out of the host galaxy and deep into the intergalactic void. They are blowtorches on a galactic scale. When these jets slam into the thin gas of the surrounding universe, they bloom into massive lobes of radio emission, creating structures that are among the largest single objects in the cosmos. A galaxy might be 100,000 light-years across, but the radio lobes powered by its central quasar can span millions of light-years. They are monuments to the power of the central engine, immense bubbles of energy inflated by a source roughly the size of a planetary system. The influence of a quasar is so profound that it dictates the fate of the galaxy around it. Astronomers have long wondered why galaxies stop growing. Why do they not keep forming stars forever until they are giant monsters of light? The answer lies in the quasar. The energy pouring out from the central black hole, the intense light, and the physical push of the jets heats up the gas throughout the entire galaxy. Stars can only form in cold, dense clouds of gas. By heating the gas, the quasar prevents it from collapsing into new stars. It acts as a thermostat, regulating the growth of its host. If the galaxy tries to feed the black hole too quickly, the quasar flares up, blasting the gas away and shutting down star formation. It is a form of cosmic feedback, a delicate balance between the creation of stars and the hunger of the central monster. In this sense, the quasar is not just a destroyer. It is a sculptor, shaping the history of the universe by limiting the size of galaxies. There is a somber beauty to this realization. The most luminous objects in the universe are also the harbingers of sterility. They shine brilliantly for a few million years, a brief period in the life of a galaxy, but in doing so, they ensure that the galaxy will eventually grow quiet and old. Our own Milky Way likely went through a phase like this billions of years ago. The supermassive black hole at our center, Sagittarius A star, is currently quiet, a sleeping giant fed only by a trickle of stellar wind. But in the deep past, it may have roared as a quasar, shaping the spiral arms and the halo of stars we see today. As we visualize the quasar, let us imagine approaching it. From a distance, it looks like a brilliant blue-white star. As we get closer, the single point of light resolves into a disk, a swirling saucer of incandescence. The color shifts from a deep, angry red on the outer edges to a blinding ultraviolet white near the center. Above and below, the jets shoot out into the blackness, narrow beams of collimated fury. The silence of space is deceptive here. If there were a medium to carry sound, the roar would be deafening, a continuous thunder of gas being torn apart by tidal forces. Time itself begins to behave strangely in this environment. According to Einstein's theory of relativity, strong gravity slows the passage of time. If we could observe a clock ticking on the inner edge of the accretion disk, we would see it moving slowly compared to our own. The light climbing out of the gravity well loses energy, shifting toward the red. It is a realm where the fundamental rules of existence, time, space, and light are warped by the presence of extreme mass. Yet, even the quasar eventually runs out of fuel. The gas in the galactic center is consumed or blown away. The accretion disk thins and fades, the jets sputter and die. The brilliant beacon dims, revealing the galaxy of stars hidden beneath the glare. The supermassive black hole remains, lurking in the dark, waiting for a wandering star or a gas cloud to venture too close, waiting to flare to life once more. But the era of the great quasars has passed. The universe is expanding, the gas is spreading out, and the great feeding frenzy of the early cosmos is over. We have seen the explosive power of the gamma-ray burst, the magnetic grip of the magnetar, and now the gravitational brilliance of the quasar. These are active powers. They are loud, bright, and concentrated. They are forces that act upon matter, heating it, crushing it, and illuminating it. They are the spectacles of the universe, the events that capture our attention and our awe. But as we drift away from the fading glow of the ancient quasars into the vast, cold spaces between the galaxies, we begin to sense something else. There is a power here that is not bright. It does not glow. It does not crush matter into singularities, nor does it twist magnetic fields. It is a power that operates in the silence and the dark. It is not a force that pulls things together. It is a force that pushes them apart. We are leaving the realm of matter and entering the realm of the void. We have spent our time examining the engines of the universe, the distinct objects that generate energy. Now, we must turn our attention to the canvas upon which these objects are painted. We must ask ourselves, what if the empty space itself is not empty? What if the vacuum possesses a power that dwarfs every black hole, every star, and every galaxy combined? The most powerful thing in the universe may not be a thing at all. It may be the universe itself. As the light of the quasar recedes into a pinprick behind us, we find ourselves alone in the expanding dark, facing a mystery that is tearing the cosmos apart at the seams. We turn now to the silent, invisible, and overwhelming force of dark energy. We have traveled from the flash of the gamma-ray burst to the crushing magnetic grip of the neutron star, and through the searing, blinding accretion disk of the quasar. In each of these instances, power was defined by concentration. It was the fury of matter squeezed into a tight space, releasing its energy in a desperate attempt to find equilibrium. These were events of noise, of violence, and of spectacle. They command our attention because they are bright against the dark. They are the storms in the ocean of the cosmos. But now we must turn our gaze away from the storms and look at the ocean itself. We drift out of the energetic core of the galaxy, past the spiral arms laced with blue stars, past the halo of ancient globular clusters, and into the deep intergalactic void. Here, the distance between galaxies is measured in millions of light years. The sky is black, save for the faint, fuzzy patches of distant island universes. It is a place of absolute stillness, a vacuum where the temperature hovers just above absolute zero. For centuries, astronomers believed that this space was merely a stage. It was a passive container, an empty box in which the drama of the universe played out. Stars and galaxies were the actors, and space was simply the nothingness that separated them. We assumed that the most important forces were the ones we could see, the gravity that pulled stars together, and the nuclear fires that pushed them apart. We believed that the universe was governed by the mutual attraction of matter, a cosmic web held together by the gravity of all things, pulling on all other things. We were wrong. In the late 1990s, two teams of astronomers set out to measure the history of the universe's expansion. We knew the universe had begun with the Big Bang and had been expanding ever since. The question was not whether it was expanding, but how quickly that expansion was slowing down. It seemed intuitive that the collective gravity of all the galaxies, all the dark matter, and all the gas in the cosmos would act as a brake. Like a ball thrown into the air that eventually slows and falls back to Earth, the expansion of the universe was expected to decelerate. The researchers hoped to measure this deceleration to determine the ultimate fate of the cosmos, whether it would expand forever or eventually collapse back in on itself in a big crunch. To measure this, they looked for standard candles, specifically a type of supernova known as type Ia. These explosions always burn with the same intrinsic brightness, allowing astronomers to calculate their distance based on how dim they appear to us. By measuring the distance to these supernovae and the speed at which they were receding, the teams could reconstruct the expansion history of the universe. What they found was not a slowing down. It was not even a steady coasting. To their astonishment, and to the shock of the scientific community, they found that the distant supernovae were fainter than they should have been. They were further away than the calculations predicted. The expansion of the universe was not decelerating under the pull of gravity. It was accelerating. The galaxies were being pushed apart faster and faster as time went on. This discovery implied the existence of a force that we had never anticipated, a force that acts in opposition to gravity, a force that does not pull but pushes. And unlike the localized power of a black hole or a star, this force does not originate from a specific point. It is not generated by an engine. It arises from space itself. We call this force dark energy. Dark energy is the ghost in the machine. It is a property of the vacuum. In our everyday experience, a vacuum is the absence of everything. If you remove the air, the dust, and the radiation from a box, you are left with nothing. But in the realm of quantum physics and cosmology, nothing is a heavy substance. Empty space possesses its own intrinsic energy. It is a simmering sea of potential, a reservoir of power that is woven into the very fabric of space-time. What makes dark energy the contender for the most powerful thing in the universe is its ubiquity. A quasar is terrifyingly powerful, but it is rare. A gamma-ray burst is intense, but it is brief. Dark energy is everywhere. It exists in the space between your eyes and this screen. It exists in the gap between the Earth and the Moon. It exists in the vast gulfs between the galaxies. Wherever there is space, there is dark energy. Its power lies in a unique and unsettling property. It does not dilute. Think of a gas in a piston. If you expand the piston, the gas spreads out, its density drops, and its pressure decreases. The same is true for light. As the universe expands, light waves are stretched, and their energy density falls. Even matter gets spread thinner and thinner as the cosmos grows, but dark energy is different. It is a constant property of space. When the universe expands, it creates more space. And because that new space comes with its own intrinsic dark energy, the total amount of dark energy in the universe increases. This creates a runaway effect. As the universe expands, there is more dark energy to push it apart. This push causes the universe to expand faster, which creates even more space, which generates even more dark energy. It is a self-reinforcing cycle of exponential growth. It is a relentless, silent tide that rises forever, lifting the galaxies and carrying them away from one another. When we calculate the energy budget of the universe, the total amount of stuff that exists, the numbers are humbling. All the stars, all the planets, all the gas clouds, all the black holes, and all the atoms in our bodies make up less than 5% of the universe. Dark matter, the invisible scaffolding that holds galaxies together, makes up roughly 27%. The rest, nearly 68 to 70% of the universe, is dark energy. In terms of sheer quantity, dark energy is the dominant component of reality. It is the ocean, and the galaxies are merely the foam on the waves. Its power is not the power of a sledgehammer. It is the power of the tide. It is slow, patient, and completely unstoppable. Gravity, the force that builds stars and galaxies, is fighting a losing battle. On small scales, like within our solar system or our galaxy, gravity is still strong enough to hold things together against the push of dark energy. The Earth will not be torn away from the Sun. The Milky Way will not be ripped apart. But on the grand scale, gravity has already lost. The implications of this silent power are profound. It dictates the destiny of the entire universe. Because of dark energy, the universe will not end in fire. It will not crunch back down into a singularity. Instead, it will end in ice and isolation. As the acceleration continues, distant galaxies will be pushed away from us faster than the speed of light. This does not violate the laws of physics, because it is the space itself that is expanding, carrying the galaxies with it. Eventually, the galaxies that are currently visible to us will cross a cosmic horizon and vanish. Their light will no longer be able to reach us against the flow of the expanding space. The observable universe, the bubble of reality we can communicate with, will slowly empty out. Billions of years from now, an astronomer on a planet orbiting a distant star might look up and see only the stars of their own galaxy. The rest of the cosmos will have been swept away by the dark energy tide. They will believe they are alone in an island universe, surrounded by an eternal empty void. The evidence of the Big Bang, the cosmic web, and the great tapestry of galaxies will have been erased by the expansion. There is a cold majesty to this force. It does not destroy matter, it simply isolates it. It is the great segregator. It ensures that the universe will become a lonely place. The fires of the quasars will die out. The gas needed to make new stars will be used up. The stars that remain will burn through their fuel and fade into white dwarfs, neutron stars, and black holes. And all the while, the space between these dead remnants will grow larger and larger. Dark energy challenges our understanding of power because it is passive yet dominant. It requires no fuel source. It generates no heat. It emits no light. It simply is. It is the cost of having a universe. It is the tension inherent in the vacuum. Some theories suggest it is the cosmological constant, a term Albert Einstein added to his equations of general relativity to keep the universe static, only to later discard it as his biggest blunder. It turns out that the term was necessary after all. The vacuum has a pressure, and that pressure is negative, acting as a repulsive gravity that pushes the fabric of space-time outward. If we were to try to harness this power, we would fail. It is not available to us. It is not energy that can be extracted to run a machine or light a city. It is the energy of the background. It is the floor upon which we stand. To access it, we would need to alter the fundamental nature of space itself. It is a power that belongs to the cosmos alone. Comparing dark energy to the other contenders we have visited is difficult. A gamma-ray burst releases more energy in 10 seconds than the sun does in its lifetime. But that energy is finite. Dark energy is, for all intents and purposes, infinite in its endurance. It will never run out. It will never stop pushing. As long as there is space, there will be dark energy. It is the only power that grows stronger as the universe ages. We often associate power with complexity. The complex nuclear reactions in a star, the complex magnetic fields of a magnetar, the complex accretion dynamics of a black hole. Dark energy is terrifyingly simple. It is a single number, a single constant that describes the springiness of space. Yet this simplicity is enough to overpower the collective gravity of every massive object in existence. It is the ultimate victory of the smooth over the clumped, the void over the matter. As we float in the intergalactic void, visualizing this force, we must imagine the space around us stretching. It is not a sensation of movement, but of becoming. There is more here than there was a moment ago. The galaxies in the distance are not moving away from us through space. The space between us and them is being generated moment by moment. We are drifting apart not because we are swimming, but because the pool is getting bigger. This is the power of the vacuum. It is the power to dictate the geometry of the universe. It determines whether parallel lines eventually meet or diverge. It determines the lifespan of the cosmos. It determines the ultimate temperature of existence. It is the silent ruler, the invisible hand that has taken the wheel of the universe and is steering it toward an eternal, frozen midnight. But is it the most powerful thing? It dominates the future. It dominates the large scale. But it is a diffuse power. It is spread thin. In any given cubic meter of space, the amount of dark energy is tiny, roughly enough to light a small dust mote. It is only when you add up all the cubic meters in the visible universe that it becomes the dominant force. It is the power of the swarm, the power of the collective. However, There is another kind of power that ripples through the fabric of space-time. Dark energy stretches the canvas, but there are events that shake the canvas. There are moments when the gravity of massive objects becomes so intense, so violent, that it does not just pull or push, it vibrates the very structure of reality. These are not steady forces like dark energy, nor are they electromagnetic flashes like gamma-ray bursts. They are tremors in the geometry of the universe. We have spoken of light, of magnetism, and of the expansion of the void. Now we must listen for the drums. We must turn our attention to the events that are so heavy they send shock waves through the fabric of reality, causing the universe to ring like a struck bell. We are moving from the silent stretch of dark energy to the rhythmic distortion of gravitational waves. Dark energy creates the distance. Gravitational waves traverse it. They are the voice of gravity itself, speaking across the cosmos. To understand this power, we must return to the black holes, but not to watch them feed. We must watch them dance. We must witness the moment when two singular objects, each containing the mass of 30 suns, spiral into one another and merge. In that fraction of a bi-second, they release more energy than all the stars in the visible universe combined, but not a single photon of light is emitted. It is a darker, deeper power. It is the power to squeeze and stretch the Earth itself, even from 1 billion light-years away. We leave the expanding silence and enter the realm of the invisible ripples. We have witnessed the universe expanding under the silent, relentless pressure of dark energy. We have seen how the vacuum itself stretches, carrying galaxies away from one another into an isolated future. This expansion is a slow, steady power, a force that works over billions of years to rewrite the map of the cosmos. But the fabric of space-time is not just a rubber sheet that stretches. It is also a drumhead that can be struck. While dark energy is the breath of the universe, inhaling slowly and deeply, there are moments when the universe screams. To hear this scream, we must turn away from the light. For all of human history, astronomy has been a science of vision. We have looked up with our eyes, then with glass lenses, and finally with electronic sensors, gathering the photons that stream across the void. We have studied the universe by watching it burn, glow, and reflect. But there is a kind of power that produces no light at all. It is a power so pure that it bypasses the electromagnetic spectrum entirely. It does not heat gas, it does not strip electrons, and it does not cast shadows. Instead, it ripples the texture of reality itself. This is the power of gravitational waves. In the early 20th century, Albert Einstein reimagined gravity not as a force pulling two objects together, but as a curvature in space and time. A massive object, like a star or a planet, sits in the fabric of the universe like a bowling ball on a trampoline, causing the fabric to dip and curve. Other objects follow these curves, creating what we perceive as orbits. But Einstein also realized that if these massive objects were to move, if they were to accelerate, spin, and collide, they would not just sit in the fabric. They would agitate it. They would send ripples moving outward at the speed of light, stretching and squeezing space as they passed. For 100 years, these waves were a theoretical ghost. We knew they should exist, but the stiffness of space-time is immense. To create a ripple that we could detect, one would need to shake the universe with violence that defies comprehension. One would need a hammer the size of a star, swinging at the speed of light. Such hammers exist. In the dark, starless voids, binary systems of black holes are locked in a death spiral. These are not the supermassive giants at the centers of galaxies, but the stellar mass remnants we met earlier, objects 20 or 30 times the mass of the Sun. When two of these ghosts find themselves gravitationally bound, they begin a dance that can last for eons. As they orbit one another, they disturb the space-time around them, losing energy in the form of gravitational waves. As they lose energy, they fall closer together. As they fall closer, they orbit faster. It is a runaway process. Imagine two objects, each darker than the night sky, each crushing 30 suns worth of matter into a sphere a few dozen kilometers across, whirling around each other hundreds of times every second. The velocity is staggering. In the final moments of their lives, they are moving at nearly half the speed of light. The space around them is whipped into a frenzy, twisted and churned by the sheer gravitational torque. Then they touch. The moment of collision, the merger, is the single most powerful event that can occur between two distinct objects in the universe. In a fraction of a second, the two black holes plunge into one another, their event horizons merging to form a single, larger, distorted black hole. This new object rings like a struck bell, shaking off the imperfections of the collision until it settles into a perfect, silent sphere. But in that brief moment of ringing, a cataclysmic amount of energy is released. Consider the mathematics of mass and energy. We know that a small amount of mass can be converted into a large amount of energy. This is the secret of the nuclear bomb and the shining sun. In a black hole merger, the conversion efficiency is terrifying. On September 14, 2015, humanity detected one of these events for the first time. Two black holes, roughly 1.3 billion light-years away, collided. One was 36 times the mass of the Sun. The other was 29. When they merged, the resulting black hole had a mass of 62 solar masses. If you do the arithmetic, you will notice a discrepancy. 36 plus 29 equals 65. Yet the final object was only 62. 3 suns worth of mass were missing. Where did it go? It did not vanish. In less than 2/10 of a second, 3 entire suns, 3 massive stars worth of matter, were instantly converted into pure gravitational energy. To put this in perspective, this is more energy than is emitted by every single star in every single galaxy in the observable universe combined. For that tiny sliver of a second, that invisible collision was the most powerful thing in creation, outshining the rest of the cosmos by a factor of 50. Yet if you had been looking in that direction with a telescope, you would have seen nothing, no flash, no explosion, no nebula. The energy was not released as light. It was released as a distortion. A tsunami of gravity raced outward from the collision, expanding in a sphere at the speed of light. It passed through the stars of its host galaxy, stretching the space between their atoms. It crossed the intergalactic void, moving silently through the dark for over 1 billion years. As the wave traveled, it spread out, its intensity diminishing with the square of the distance. By the time it reached the Milky Way, it was a whisper. It passed through our solar system, through the Earth, and through our bodies. As the wave passed, it physically stretched the space we occupy. For a fleeting moment, the Earth became slightly wider and slightly flatter, then taller and narrower, oscillating as the ripple went by. The scale of this distortion is incredibly small. The wave stretched our planet by less than the width of a single proton. It is a testament to the rigidity of space that an event releasing the energy of 3 suns could only ripple our world by such a microscopic amount. but we felt it, or rather, our machines did. To detect this power, humanity built the most sensitive ears in history, the Laser Interferometer Gravitational Wave Observatory, or LIGO. These huge installations consist of 2 concrete arms, each 4 kilometers long, arranged in an L shape. Inside these arms, in a near-perfect vacuum, laser beams bounce back and forth between mirrors. The lasers are used to measure the length of the arms with a precision that borders on the impossible. They are looking for a change in distance smaller than 1,000th of the diameter of a proton. When the wave from that distant collision passed through the Earth, it lengthened one arm of the detector and shortened the other. The laser beams drifted out of alignment, creating an interference pattern, a flicker of light on a sensor. This data, when converted into sound, produced a short, rising tone, a chirp. That chirp was the sound of 30 solar masses crashing into 29 solar masses at half the speed of light. It was the death cry of 2 black holes and the birth cry of a new one. It fundamentally changed our relationship with the universe. We were no longer just watching a silent movie. We had turned on the sound. The power of gravitational waves lies in their ability to pass through anything. Light can be blocked by dust, X-rays can be absorbed by gas, but gravity couples to everything. A gravitational wave can pass through the core of a star, through the center of a planet, through the dense heart of a galaxy, and emerge the other side completely unchanged. Nothing can shield you from gravity. It is the only force that is truly transparent to the entire cosmos. This transparency means that gravitational waves carry the purest information about the most violent events. They allow us to see inside the event horizons of merging black holes, to probe the dense nuclear slush of colliding neutron stars, and potentially to look back to the very beginning of time. While black hole mergers are invisible to the eye, there are other collisions that light up the sky. When 2 neutron stars, those dense, city-sized magnets we visited earlier, collide, they produce both gravitational waves and a blast of light. This is a kilonova. In these events, the power of gravity is used to forge the heaviest elements in the universe. The gold in your wedding ring, the platinum in your catalytic converter, the uranium in our reactors. These atoms were likely created in the crushing, twisting, heated mess of 2 neutron stars merging. In a kilonova, we see the union of all the powers we have discussed. We have the density of the neutron stars, the magnetic fury of their fields, the flash of gamma rays as the jets break out, and the ripple of gravitational waves shaking the cosmos. It is a symphony of physics, a moment where the universe flexes every muscle it has. But the pure black hole merger remains the king of invisible power. It is a reminder that the universe is not made of objects, it is made of fields. The black holes themselves are just curved knots in the gravitational field. When they merge, it is geometry interacting with geometry. It is a storm in the fabric of space-time itself. There is a philosophical weight to this power. We often think of powerful things as being large and bright, but the gravitational wave teaches us that the greatest release of energy can be totally dark. It teaches us that space is not nothing. It is a medium that can carry energy. A gravitational wave is energy, stripped of all matter. It is a traveling disturbance in the structure of reality. If you were close to such a merger, say a few thousand kilometers away, the gravitational waves would not just be a scientific curiosity. They would be lethal. The stretching and squeezing of space would act on your body. You would be pulled apart and compressed, oscillating thousands of times a second. The friction generated within your own tissues by this stretching would heat you up. You would not be burned by fire. You would be boiled by the warping of space itself. It is a horrific and awe-inspiring thought, to be destroyed not by heat or impact, but by the changing geometry of the place you occupy. As the wave moves on, leaving the new, larger black hole behind, the universe returns to a semblance of calm. The ringing fades. The new event horizon smooths out, becoming a perfect sphere of darkness. The energy released travels outward forever, a permanent record of the event. We have now seen the full spectrum of cosmic power. We have seen the blinding electromagnetic flash. We have seen the magnetic distortion. We have seen the gravitational furnace of the quasar. We have seen the relentless, quiet push of dark energy. And now we have seen the violent trembling of space-time. Each of these candidates holds a claim to the title of most powerful. The gamma-ray burst dominates brightness. The magnetar dominates intensity. Dark energy dominates the total budget. Gravitational waves dominate the instantaneous release of energy. But all of these things, the stars, the black holes, the magnetic fields, the space-time fabric itself, had to come from somewhere. They are all effects, consequences of a prior cause. They are the shrapnel of a much larger explosion. They are the cooling embers of a fire that burned so hot it created the laws of physics themselves. To find the true champion, the undisputed source of all power in the cosmos, we must wind the clock back. We must reverse the expansion of dark energy. We must separate the black holes. We must uncollapse the stars. We must go back before the light, before the gravity, before the silence. We must return to the moment when the clock started. We must return to the singularity. In our final step, we will journey to the beginning of time to witness the event that contained all the energy that will ever exist, compressed into a point smaller than a single atom. We are going to the Big Bang. We have reached the end of our journey through the geography of cosmic power. We have stood in the beam of the gamma-ray burst, felt the magnetic shearing of the magnetar, watched the voracious feeding of the quasar, drifted on the expanding tide of dark energy, and listened to the ringing of the gravitational bell. Each of these phenomena represents a pinnacle of physical extremism. They are the giants of the modern universe, the engines that drive the evolution of the cosmos. But as we noted, they are all effects. They are the secondary and tertiary consequences of a much older, much deeper event. To find the true source of all power, the absolute zero point from which every joule of energy in existence flows, we must leave the present day behind entirely. We must reverse the arrow of time. Imagine the movie of the universe playing backward. The galaxies currently flying apart under the influence of dark energy begin to rush toward one another. The vast voids shrink. The light of the quasars is extinguished as the gas flows back out of the black holes. The stars unexplode, gathering their scattered dust back into swirling nebulae, then collapsing back into hot blue spheres. The heavy elements, the gold, the iron, the carbon, break apart into simple hydrogen and helium. As we continue to rewind, the universe becomes smaller, hotter, and denser. The majestic spiral galaxies dissolve into a uniform fog of gas. The transparency of space vanishes, replaced by a blinding, glowing plasma that blocks all vision. We are pushing back past 13 billion years, past the formation of the first stars, into the dark ages, and further still, into the first few minutes of existence. The universe is now a searing soup of particles, a place where temperatures are so high that atoms cannot hold together. Protons and neutrons are smashed apart into a quark-gluon plasma, a fluid of fundamental building blocks. The forces of nature, gravity, electromagnetism, and the nuclear forces begin to merge, losing their distinct identities. We are approaching the wall. We are approaching the moment of the singularity. Here, at the mark of time equals 0, we encounter the limit of our understanding and the beginning of everything. This is the Big Bang. It is a common misconception to picture the Big Bang as an explosion in space. We tend to imagine a black void, empty, and waiting, and then a spark that ignites a fireball expanding into that darkness. But this is wrong. There was no space outside for the universe to expand into. There was no time before for the event to happen in. The Big Bang was not an explosion in space. It was an explosion of space. At that singular moment, all the matter and energy that currently spans 93 billion light years was compressed into a point smaller than a single atom. It was a point of infinite density and infinite temperature. In this state, the laws of physics, as we know them, did not exist. There was no up or down, no cold or hot, no future or past. There was only potential. If we are looking for the most powerful thing in the universe, we must look at the mechanism that took this microscopic knot of potential and blew it up to become the cosmos. This mechanism is a specific phase of the early universe known as cosmic inflation. Inflation is the heavy lifter of creation. It occurred in the tiniest fraction of a second after the clock started, specifically between 10 to the power of minus 36 and 10 to the power of minus 32 seconds. These are numbers so small, they are meaningless to the human mind. It is a slice of time so thin that it makes a nanosecond look like an eternity. During this brief window, a mysterious energy field, often called the inflaton field, dominated the universe. This field possessed a property similar to the dark energy we see today, but exponentially stronger. It exerted a repulsive force of unimaginable intensity. It grabbed the fabric of space and stretched it. The rate of this expansion is the definition of power. In that fraction of a second, the universe doubled in size, then doubled again and again, repeating the process nearly 100 times. It went from the size of a subatomic particle to the size of a grapefruit in less time than it takes for light to cross the width of a proton. This expansion was faster than the speed of light. This does not violate the laws of physics, because it was space itself expanding, not objects moving through it. This inflationary expansion smoothed out the universe. Any wrinkles, any knots, any irregularities in the initial texture of space were stretched until they were flat. It is why the universe looks the same in every direction today. It was an event of absolute homogenization, but the true display of power came when inflation stopped. The energy that drove this rapid expansion could not just disappear. The law of conservation of energy dictates that energy can change form, but it cannot be destroyed. When the inflaton field turned off, its energy had to go somewhere. It went into the vacuum. This process, known as reheating, is arguably the most energetic event that has ever occurred. The potential energy of the inflation field collapsed and dumped itself into the fabric of space, instantly creating a sea of particles. Quarks, electrons, neutrinos, and photons flooded into existence. The cold, expanding vacuum was suddenly filled with a fire of 10,000 trillion degrees. This was the true bang. It was the conversion of the energy of space into the energy of matter. Every single particle in your body, every photon of light emitted by every star, every atom in the Earth's core, all of it traces its lineage back to this moment of reheating. The power of the Big Bang was the power of materialization. It was the moment the universe decided to be something rather than nothing. As the universe continued to expand, albeit at a slower, more sedate pace, it began to cool. The fire of creation dimmed. The quarks bound together to form protons and neutrons. The protons and neutrons caught electrons to form the first atoms of hydrogen and helium. And then, about 380,000 years after the beginning, the universe became transparent. The light that had been trapped in the hot plasma was finally released. It streamed outward in all directions, a flash of white light filling the entire cosmos. Today, 13.8 billion years later, that light is still traveling. It has been stretched by the expansion of space until it is no longer visible light, but microwave radiation. We call this the cosmic microwave background. If you have ever tuned an old analog television to a dead channel, a small percentage of that static, the chaotic snow dancing on the screen, is caused by this ancient light. You are watching the afterglow of the Big Bang. You are seeing the oldest ghost in the universe. The cosmic microwave background is a fossil. It is a map of the power distribution of the infant cosmos. When we look at it with our most sensitive satellites, we see that it is almost perfectly uniform. The temperature is the same in every direction to within 1 part in 100,000. This uniformity is the smoking gun of inflation. It proves that the entire visible universe was once a single, connected point before it was blown apart. However, the map is not perfectly smooth. There are tiny microscopic fluctuations, spots that are slightly hotter or slightly colder than the average. These tiny ripples are the seeds of everything we see today. They are the quantum fluctuations of the early universe, magnified by inflation onto a cosmic scale. The slightly denser spots had slightly more gravity. Over billions of years, they pulled in more matter. They grew into gas clouds, then into stars, then into galaxies, and finally into the vast cosmic web we observe today. We are living in the echo of the Big Bang. The power that forged the hydrogen in the water you drink was the power of that first few minutes. The expansion that carries the distant galaxies away from us is the continuation of the push that started it all. The gravity that holds your feet to the floor is the result of the curvature created by the mass born from that initial energy. So, when we ask, what is the most powerful thing in the universe? The answer is complex. If we mean the brightest flash, it is the gamma-ray burst. If we mean the strongest field, it is the magnetar. If we mean the most efficient engine, it is the quasar. If we mean the most dominant force, it is dark energy. If we mean the most violent vibration, it is the gravitational wave. But if we mean the source, the origin, the singular event from which all other power flows, then the answer is the Big Bang itself. It is the only event that involved all the energy and all the space in existence. It did not just happen in the universe, it was the universe happening. There is a profound humility in this realization. We are small, fragile beings living on a dust mote circling a modest star in a quiet corner of a galaxy. Yet, we are connected to this ultimate power. The atoms in our hands were forged in the cooling fire of the Big Bang and cooked in the hearts of stars. The energy that powers our brains is chemical energy. derived from the plants we eat, which gathered sunlight, which came from the fusion of hydrogen, which was created in the first 3 minutes of time. We are not separate from the power of the universe. We are a shape that power has taken. As we conclude our search, we can look up at the night sky with a new perspective. We are looking at a cooling landscape. The universe is a heat engine that is slowly running down. The fury of the Big Bang has dissipated into the gentle warmth of stars and the cold microwave background. The era of the great quasars has passed. The rate of star formation has peaked and is declining. We are living in the autumn of the cosmos, a time of golden light and stability.